In this problem, we have a spherical, I guess you could say shell, but this one actually has a thickness in the middle of it here. And our goal is to find the electric field in a couple different regions. The first region that we're going to try to find it for is on the inside in here. The second one would be in between these two shells, and the last place is on the outside right here. One information that's pretty good to know is that on the inside right here, the charge density goes like this. It goes like 1 over r squared with some sort of constant k, where constant k is just some sort of known constant. Additionally, another thing that's good to know is that the radius from the center all the way out to the outer shell is equal to b, and then the radius from the inner point to the inner shell is equal to a right now. So the first step is to try to figure out what is the electric field when r is less than a, also known as the on the inside of it right here. And that's pretty simple. If you went back and we did all the problems that we did before, we know that the electric field inside a symmetrical spherical shell right here is equal to 0, actually. And if you're confused about that, I recommend going back in some of the earlier chapters or the earlier problems in this chapter, but that was a pretty easy one to knock out just by inspection. We know that for everywhere that their electric field, there's going to be an equal and opposite one, assuming that the charge density is symmetrical, in which it is in our spherical coordinates that we have right here, where r hat points away from the main center point here. So the next part that we need to concentrate on is between A and B. So not quite touching, but we know that it's going to be somewhere in the middle. So if we did a Gaussian surface, this is the Gaussian surface chapter, we put a Gaussian surface in between these two, which is right in the middle of this charge density I have right here. And I guess I should do this. This is always a good thing to note, and that is a highlighter. And this is always a good thing to note, is whenever you do, it's always good to try to put rho as a function of r for us to make sure that we know we're going to have to do some extra steps right here, but it's not hard, and it's definitely something that we can do. So in order to find that, we're going to go ahead and put our Gaussian surface right here in the middle of the two shells, and since the Gaussian surface is going to be a sphere, again, like this is just a cross section right here, right? This is actually a whole sphere, but we put a sphere that is somewhere in between these two, arbitrarily in between those two, at a radius of r. And then we're going to go ahead and try to find out what the electric field is here. So we'll just go ahead and set up Gauss's law. So we just dot the electric field, which is symmetrical in the r hat direction, with the surface, the Gaussian surface that we have, which is of course symmetrical because it is symmetrical in respect to r. The normal vector of our circle also points in the direction of the electric field, which allows these dots to turn into just a multiplication, and then that is proportional to our q that's enclosed, and our proportionality constant 1 over epsilon naught. And one thing that's good to note right now is that we can go ahead and see that this is actually going to be the volume integral of that rho, which is a function of r, and the volume that's closed inside. We'll go ahead and set that up next, but we'll go ahead and look at this the surface integral right here, and since these are both in the r hat directions, this dot just ends up becoming a multiplication of the magnitudes of those two. So we have the magnitude of the electric field, which is what we're looking for. Well, I guess specifically we're looking for the electric field with the direction, but we'll get to that later. But right now we'll solve for the magnitude. And we'll do the the volume integral right here. And since we're working with spherical coordinates, since we have spherical symmetry right here, a bunch of spheres, we can go ahead and do that. And we know it's going to be dr, and since r is pretty much taken, we can go ahead and just label r as s, as we to be consistent with the rest of the problems that we did in the earlier chapter. So this is the volume element for our Gaussian surface right here, or that which is contained in the Gaussian surface. And we're going to integrate this differential volume space over all the space. So for phi, it's going to be from 0 to 2 pi, because it sweeps around in one big circle. For d theta, it sweeps from this one all the way down to here, so that's pi 0 to pi. And then for this problem, we're just going to go from, we're going to go from a to r, right? So that's consistent with right here. So we're just going to go to a to r. If we don't need to necessarily integrate, I guess we could integrate from here to here. It does encompass everything that's on the inside here, but there's nothing inside. So we don't really need to start our integral until the radius of a, because that's when the charge starts in accordance with the problem. So we'll go ahead and do that. And then, of course, our rho that we're integrating is k over r squared. But since we're integrating to r, we're just going to go ahead and change r to s, just so we can stay consistent and not lose things. You could call this r prime, curly r, whatever, but I just prefer to do it s to be explicit. So let's go ahead and move this over to this side and just clump all the constants out in front. So that is equal to 1 over 4 pi epsilon naught. And then we have the constant k, and then the r squared. I just like to keep the 4 pi epsilon out in front because it's it's just kind of good to work with, since it's that's the common form for electric fields. And so what we can go ahead and do, and since there's no thetas necessarily here, we can go ahead and just do the sine and all these angle L integrals right here, and that'll end up being 4 pi. And you can go ahead and check that with the math, but it's going to be a common thing for us to do. And we're still left with the radial integral of, which is s squared, which is just one fairly easy integral for us to go ahead and accomplish. So we'll go ahead and do that now. Let's see here. I'll go ahead and drop the, oh, you know what? Right now, I'll just go ahead and take the magnitude signs off, and because we know that the electric field, because of spherical symmetry, the electric field's always going to be pointing outward in the radial direction. So I can go ahead and just drop this r. I'll move it over later, but I know it's going to be in the r hat direction. All right, so we have our k, r squared, and then we have our 4 pi right there. And then the integral is just equal to r minus a, right? And now we can go ahead and start getting this into, I just like to massage it into a form. Let's go ahead and bring this little guy over. No need to be shy. I like to massage this into a form that is very similar to forms like a point charge, because it can help, enlighten us about the way it behaves in the future and stuff. So as you can see, this is like a point charge, except I could have easily gotten rid of the 4 pi here, and you can too, but I just like to leave the 1 over 4 pi epsilon naught because I like to compare it to a point charge. So it looks like something that has to deal with like the surface area of a sphere, and has something to do with the radiuses, and of course some sort of a constant out in front there, but we know it's pointing in the r hat direction. The important thing to note is that this thing it goes like r minus a r squared, and if we were to plot it, which we will in the future, it's going to look something like this, where if this is the electric field magnitude and this is the r, the electric field will be, if you plotted it, it would go like this, and it would cross the axis at r equals a right here, and then it kind of asymptotes out here. And we're going to be needing that for the last part of this problem, but for the second to last part of this problem, we'll go ahead and just start it now, because now we're looking at the electric field on the outside of this whole shell. And so let me go ahead and just copy this down right here for us to use. Actually, I'll be doing a lot of this next part is going to go really fast, so I'm just going to go ahead and copy this down for reference. So if we're looking at the electric field on the outside part here, we're going to be doing essentially the same thing. We're going to be doing a surface integral of the enclosed surface area integral of the electric field dotted with our Gaussian surface, and in this case the Gaussian surface is still at a radius r. This is still a radius r, but encompasses everything here. So since it has spherical symmetry and not equal to, so these that dot product will end up turning into a multiplication just like the rest of it, except the only thing is that we're going to integrate from a all the way out to b. Well, technically we're integrating from r equals a all the way out to wherever r is, But since there's nothing on the outside here and all the charges encompasses here, we can just stop our integral between a and b. Those are our integral limits. So what you'll notice is that it's going to be, our next step is going to be the same thing that we did all the way up here, except we're going to change our integrals, our integral limit, which our integral limits are not going to be changing much about the problem itself. So I'll go ahead and change those, but I'll make the edits in orange. So remember, we're integrating from a to b, all right? And so this means that this was going to change a to b. I mean, we're still at an a, but it doesn't really change much. So all this stuff stays the same. All this just stays the same. We're still integrating this very easy function right here. And so this part will change right here. It's just the same steps. Let me see here. B minus a and b minus a. Right, and so this is actually a really cool portion to think about, because now this is proportional to, let's see, so it's proportional to like a bunch of constants, but it's really just 1 over r squared, right? So 1 over r squared looks something like this, right? So it's gonna, well, I mean, better than that. Kind of asymptotically drops over. This is why I use computer software. But the last part of the problem actually asks us to plot everything. So I'm going to go ahead and just make room right here. So this is the last part of the problem. The last part of the problem asks us just to plot this, right? And let me go ahead and make these axes clear. Right, so we know that there's some main points right here. So the first portion is going to be on the inside of all this stuff, all the way from 0 all the way out to a. So that is going to be equal to, let me go ahead and write it explicitly in here. We'll just mark this a, right? And then we're going to undergo some sort of change right here as we're inside of the two spherical shells, that little all those shells. So something happens between a and b. And then finally, we evaluate the electric field from here. And then the further we go out, nothing really changes much except the distance away from it. We're not encountering more charges. So we have 3 specific regions that we are going to look at in terms of the plot. And luckily, we did all that stuff beforehand. So when we look at from 0 to a, everything on the inside, if we scroll back up, we already found this out. The electric field on the inside is just equal to 0. So I'm just going to go ahead and write it in orange. So our electric field is 0 right here. And then in between all this stuff, we found that out. We found that the plot kind of looks like this, right? Where it starts off at A and kind of asymptotically peels off right here, because it's proportional to like some global constants, right? Some global constants, but this is what actually makes the variable portion right here. So we can go ahead and just start at A, and then it kind of peels off like that. And then finally, this is what we had right here. Everything other than the r squared is just a constant, but what we're left with right here is just 1 over r squared for everything that's on the outside. And that makes sense, right? That's like what we typically encounter for any sort of charges. As long as we take the electric field further and further away, it's going to drop off like 1 over r squared, the electric field. So that's exactly what we have here, is that it starts right here, and then it peels off right here. And that's our plot. It seems to make sense, right? So we have nothing, nothing, nothing as we move out here, and then we get a bunch of charge here, but since it drops off like 1 over r squared, the electric field slowly, it slowly tapers off, and then once we get outside of the spherical charge here, it drops off big time, like 1 over r squared. And that is exactly what we have right here, and everything seems to make sense.